14.2. Variation of pressure with depth. The outline of this video is as follows. First, we will derive the fundamental equation that relates the pressure within a fluid to its depth. This will show us precisely how pressure increases the deeper you go. Next, we will introduce a crucial concept known as Pascal's law, which describes how a change in pressure is transmitted uniformly throughout an enclosed fluid. We will see how this principle is the foundation for hydraulic systems, which cleverly use fluids to multiply force. To solidify these ideas, we will then work through several practical examples. These will include analyzing a hydraulic car lift, calculating the pressure on a person's eardrum at different water depths, and determining the total force exerted on a dam. To understand how pressure changes within a fluid, we first need to discuss the concept of density. You have likely experienced this pressure variation yourself. Divers feel the water pressure increase as they go deeper, while atmospheric pressure decreases at higher altitudes. The key physical property that governs this change is density. Density, represented by the Greek letter rho, is defined as a substance's mass divided by its volume. For the liquids we will study, we will assume they are incompressible, which means their density is uniform throughout. This is quite different from gases, which have densities about 1/1000th that of liquids under normal conditions. This difference implies that the average spacing between molecules in a gas is about 10 times greater than in a liquid. Understanding density is the first step to calculating how pressure changes with depth. To understand how pressure changes with depth, we will analyze the forces acting on an imaginary block, or parcel, of fluid. This approach allows us to apply Newton's laws to the fluid itself. Let us consider a cylindrical parcel of fluid with height h and cross-sectional area a. This parcel is at rest within the larger body of fluid, so it is in static equilibrium. We need to identify all the vertical forces acting on it. First, the fluid above the parcel pushes down on its top surface. This force equals the pressure at the top, P0, multiplied by the area A. Second, the fluid below the parcel pushes up on its bottom surface. This upward force is the pressure at the bottom, P, times the area A. Finally, gravity pulls the parcel itself downward. This force is its weight, which is its mass times g. We can express the mass as the density, rho, times the volume, which is A times h. These three forces must balance for the parcel to be in equilibrium. This slide shows how we derive the fundamental equation for pressure as a function of depth in a fluid. This relationship is crucial for understanding how pressure behaves in liquids, from the depths of the ocean to the fluid in a hydraulic lift. We begin by applying Newton's first law to a parcel of fluid in static equilibrium. Because the parcel is not accelerating, the net force on it must be zero. In the vertical direction, there are three forces: an upward force on the bottom surface equal to pressure P times area A, a downward force on the top surface equal to P0 times A, and the downward force of the parcel's own weight, which is mass, m times g. Next, we can express the mass, m, in terms of the fluid's density, rho. Mass is density times volume, so m equals rho times A times h. Substituting this into our force equation and canceling the area A from every term allows us to solve for P. The result is the pressure depth equation. P equals P0 plus rho times G times H. This tells us that pressure increases linearly with depth. The pressure at any point is simply the pressure at the surface plus an amount that depends on the fluid's density and the depth. This slide introduces a fundamental principle of fluid statics known as Pascal's law, which explains how we can use fluids to multiply force. The law states that a change in the pressure applied to an enclosed fluid is transmitted undiminished to every point within that fluid and to the walls of the container. It is important to note that this applies to the times change times in pressure, not the absolute pressure, which still increases with depth. The classic application of this principle is the hydraulic lift. Imagine a sealed system with two pistons of different sizes. If you apply a small force to the small piston, you create a pressure increase. This exact same pressure increase is transmitted through the fluid to the larger piston. Since pressure equals force divided by area, that same pressure acting on a much larger area produces a much larger output force. Essentially, Pascal's law allows a small input force to generate a large output force, forming the basis for hydraulic brakes and car lifts. A classic and powerful application of Pascal's law is the hydraulic lift, which allows us to multiply an applied force. Let us see how this works. We start by applying an input force, which we call F1, to a piston with a small surface area, A1. This action creates A pressure within the enclosed, incompressible fluid. This pressure, P, is equal to the force F1 divided by the area A1. According to Pascal's law, this pressure is transmitted equally throughout the entire fluid. This means the same pressure also acts on a second, larger piston with a surface area of A2. This pressure generates an output force, F2, on the larger pistons. Since the pressure is the same on both sides, we can set the two expressions equal. F1 over A1 equals F2 over A2. A common example is a hydraulic car lift, where a small force on a narrow piston generates enough pressure to lift a heavy car on a much wider piston. By rearranging the equation, we see that the output force F2 is the input force F1 multiplied by the ratio of the areas, A2 over A1. This means a small input force can generate a large output force simply by making the output piston's area larger than the input piston's area. While a hydraulic lift provides a significant mechanical advantage, it must still obey the law of conservation of energy. We can demonstrate this by looking at the work performed. Because the hydraulic fluid is incompressible, the volume of fluid displaced by the small input piston, V1, must equal the volume that moves the large output piston, V2. Since volume is area times displacement, this means A1 times delta x1 equals A2 times delta x2. From our previous discussion of Pascal's law, we know that the ratio of the forces, F2 over F1, equals the ratio of the areas, A2 over A1. By combining these two relationships, we find that F1 times delta x1 equals F2 times delta x2. This is a very important result. The quantity force times distance is work. This equation shows that the work you put into the system is exactly equal to the work you get out. This means you must trade force for distance. To lift a very heavy car a small distance, you have to apply your smaller input force over a much larger distance. In short, a hydraulic lift does not create free energy. It simply changes how that energy is applied. Let us apply our understanding of how pressure varies with depth to a quick conceptual question. We are asked to compare the pressure at the bottom of a glass when it is filled first with water and then with ethyl alcohol. The key relationship here is the equation for pressure at a certain depth. P equals P naught plus rho times G times H. In this problem, the depth H is the same because the glass is filled in both cases. The atmospheric pressure at the surface, P naught, and the acceleration of gravity, G, are also constant. The only factor that is different between the two scenarios is the density of the fluid, represented by the Greek letter rho. The slide gives us the densities. Water has a density of 1,000 kilograms per cubic meter, while ethyl alcohol has a density of 806 kilograms per cubic meter. Since pressure is directly proportional to density, the less dense fluid will create less pressure. Therefore, the pressure at the bottom of the glass filled with ethyl alcohol is smaller than the pressure from the water. Let us apply Pascal's law to a common real-world device, the hydraulic car lift. This example shows how we can use fluid pressure to multiply force. The problem asks for the input force, F1, on the small piston required to lift a car weighing 13,300 newtons. This weight is the output force, F2. The core principle here is Pascal's law, which states that the pressure is the same on both pistons. This means the force F1 divided by area A1 must equal the force F2 divided by area A2. To find the unknown input force, we can algebraically rearrange this equation. F1 is equal to F2 multiplied by the ratio of the areas, A1 over A2. Because the pistons are circular, the area is pi times the radius squared. This means the ratio of the areas is simply the ratio of the radii squared. Plugging in the given radii and the car's weight, we calculate an input force of approximately 480 newtons. Notice how a force of less than 500 newtons can lift an object weighing over 13,000 newtons. This force multiplication is the key advantage of a hydraulic lift. For the second part of the car lift problem, we need to find the air pressure that produces the input force we just calculated. This is a direct application of the definition of pressure. Pressure is defined as force per unit area. So the required pressure, P, is equal to the input force, F1, divided by the area of the small piston, A1. We substitute the force we found in the previous step, 1.48 times 10 to the power of 3 newtons. We then divide this by the area of the small piston, which is pi times the radius of 5 times 10 to the power of -2 meters squared. Performing this calculation gives us a pressure of 1.88 times 10 to the power of 5 pascals. To give this some context, standard atmospheric pressure is about 1 times 10 to the power of 5 pascals. So the required air pressure is almost twice the pressure of the air we are normally in. Let us apply our understanding of pressure and depth to a common experience: the feeling of pressure in your ears when you swim to the bottom of a pool. This example calculates the net force on an eardrum at a depth of 5 meters. The key is to find the net force, which is caused by the pressure difference between the water outside and the air inside your middle ear. We assume the air inside is at normal atmospheric pressure. First, we calculate this pressure difference, which is the gauge pressure, using the formula ρ times g times h. For water, with a density of 1 times 10 to the power of 3 kilograms per cubic meter and a depth of 5 meters, the pressure difference is 4.9 times 10 to the power of 4 pascals. Next, to find the force, we multiply this pressure difference by the area of the eardrum. We can estimate the eardrum's area to be about 1 square centimeter, which is 1 times 10 to the power of -4 square meters. Multiplying this pressure by this small area gives a force of approximately 5 newtons. This force is roughly the weight of a 1-pound object, which is quite significant for such a delicate membrane. This calculation explains why swimmers feel discomfort and need to pop their ears to equalize the pressure on both sides of the eardrum. Let us work through an important example: finding the total force that the water behind a dam exerts on its face. This problem is a great application of our pressure-depth relationship, but it comes with a challenge. The pressure is not constant over the entire face of the dam. It is lowest at the surface and greatest at the bottom. Because of this, we cannot simply calculate the force by multiplying a single pressure value by the dam's total area. To solve this, we must use calculus. The strategy is to divide the large area of the dam's face into many infinitesimally thin horizontal strips. For each individual strip, the pressure is essentially constant. We can then calculate the small force on each strip and add up all those forces using an integral. Let us define our variables for one of these strips. Imagine a strip at a height y from the bottom of the dam, with a tiny vertical thickness of dy. The depth of this strip, measured down from the water's surface, is h, which is equal to the total water height h minus the strip's position y. This setup is the key to finding the total force on the dam. To find the total force on the dam, we must sum the individual forces acting on all the infinitesimally thin horizontal strips. This summation is precisely what an integral does. We start with the expression for the differential force, dF, on one strip, which is rho times g times the quantity h minus y, all multiplied by w dy. To get the total force F, we integrate this expression from y equals 0 at the bottom of the dam to y equals h at the water's surface. The terms rho, g, and w are all constants, so they can be moved outside the integral. We are left with integrating the quantity h minus y. The integral of h with respect to y is h times y, and the integral of y is y squared over 2. Now, we evaluate this result at the limits. Plugging in the upper limit, h, gives h squared minus h squared over 2. The lower limit of 0 contributes nothing. The expression in the brackets simplifies to 1/2 h squared. The total force exerted by the water on the dam is 1/2 times rho times g times w times h squared. Let us consider if we could have solved for the force on the dam without using calculus. It turns out we can, and the key insight is that fluid pressure increases linearly with depth. Because the pressure grows in a straight line from 0 at the surface to its maximum value at the bottom, we can use the average pressure over the entire face of the dam. The average pressure is simply the arithmetic average of the pressure at the top and the pressure at the bottom. The pressure at the top is 0, and at the bottom depth h, it is rho times g times h. Averaging these gives 1/2 rho gh. The total force is then this average pressure multiplied by the total area of the dam's face, which is its width times its height, h. Multiplying these together gives a final force of 1/2 rho g wh squared. This is the exact same result we found using integration, providing a great intuitive check on our answer. Let us now summarize the key principles governing pressure in a static fluid. First, we established that pressure increases linearly with depth. This is captured by the equation P equals P naught plus rho gh, where P naught is the pressure at the surface and h is the depth below it. A direct consequence of this is Pascal's law, which states that a change in pressure applied to an enclosed fluid is transmitted undiminished to every point throughout the fluid. We then explored a powerful application of this principle, the hydraulic lift. By applying a small force to a small area, we can generate a much larger force on a larger area, with the force multiplication equal to the ratio of the areas. Finally, we touched on the more complex case of calculating the total force on a submerged vertical surface. Because pressure varies with depth, this calculation requires us to integrate the pressure over the entire area or use the average pressure. To wrap up, let us consider 2 review questions that will help solidify these concepts. The first question involves a hydraulic lift, which is a classic application of Pascal's law. You are asked to calculate the output force given the piston radii and an input force. Remember that the pressure is transmitted equally throughout the fluid, so the pressure on the small piston equals the pressure on the large piston. The question also asks about energy conservation. Think about the work done on each piston. While the forces are different, the work done must be the same, which means the distances the pistons move are also different. The second question asks you to explain why a dam is built to be much thicker at the bottom. To answer this, think about how fluid pressure varies with depth. The pressure at the bottom of the reservoir is much greater than the pressure at the top. Therefore, the total force exerted by the water is greatest at the base, requiring a thicker structure to withstand it. I encourage you to pause and work through these questions to test your understanding.